All right, you guys, welcome to our last unit of AP Physics 1. We're going to start by taking some notes, but this is vocabulary that you need to know. So this is on the inside cover of your new packet. So I just want you to take notes on this, which I know is not very exciting. But then I'm going to give you examples, and I want you to keep this terminology next to while I give you the examples. Okay, so the length of a spring that is neither stretched nor compressed. I've heard it called as the natural length. Whoops. The natural length of the spring, or the relaxed length. Okay, so that means the spring is neither stretched nor compressed. Rarely do you need to know the length of the spring, but we're just talking about the way it naturally rests. Okay, so the time it takes for an object connected to the spring to make one full cycle, you've actually heard this word before, it's called period. Period is the time for one full cycle, so one full rotation. We did this in circular motion, or one full oscillation, so I'll give examples of that. The letter that we used for period is a capital T. So that's what we call our variable. And period is the time it takes. So the units are seconds. By the way, we use a lowercase t for time, but we use an uppercase T because this is a special time. Okay, let's keep going. All right, so the maximum, come back here. The maximum displacement from equilibrium. So I'll show you what equilibrium is in a moment. But basically that's when the spring, the end of the spring, is at its relaxed length. But I'll give examples of this. So displacement, that's a vector. So that's distance and direction. So we use plus and minus signs for direction if we're in one dimension, or you can say right or left, and I'll give examples of that. And it does say a particle or waves vibration. Waves are so cool, but unfortunately we do not do that in AP1. Anyway, this is called the amplitude. Okay, so the amplitude is the maximum displacement to the left or right of the object attached to the spring. The variable that we use for amplitude is an A. I've also seen it as X max, like if a box is connected to a spring on a horizontal frictionless surface. And the unit that we use, well, it's a displacement, and displacement is distance, including direction, so we use meters. Okay. Now I'm going to add a little bit to this. A force that is directly proportional to the, I'm going to cross out amplitude and write displacement. Okay, that is always pointing back towards equilibrium. So this doesn't mean much now, but when I give you examples, hopefully this will make more sense. That is called a restoring force. Okay, so whenever there's a force that wants to bring an object back to essentially its lowest energy, it's called a restoring force. And with springs, we're moving in a straight line, so that would be a linear restoring force. But there also is a torque, a restoring torque. And I will show that for pendulums, because the force of gravity on the object that we are swinging back and forth in front of us is applying a torque to bring it back towards equilibrium. Okay, let's keep going. The number of cycles completed per second. That also could be the number of rotations completed per second. That is called frequency. And the variable that we use for frequency is a lowercase f. And the units we use for frequency is 1 over seconds, because cycles isn't a unit, which is also called a hertz. And by the way, that's abbreviated as Hz. And it's worth knowing that frequency, which is the cycles per second, is the inverse of the period, which is the time per cycle. So this is the time per cycle. And this is, or the seconds per cycle, you could think of it as, and this is the cycles per second. Okay, so they are inverses. Okay, the last one, and this is the title of our current unit: repetitive movement back and forth through an equilibrium position caused by a linear restoring force. That is called simple harmonic motion. And we could also replace force or linear force with torque in the case of a pendulum. Okay, but I don't want to rewrite that whole statement. So repetitive movement back and forth through an equilibrium position caused by a restoring torque is simple harmonic motion. And my N does not look like an N here. I'm going to rewrite that. And by the way, I routinely abbreviate this as simple harmonic motion. And I don't want this. There we go. Get rid of it. Okay, so right now the box is at equilibrium position. Okay, if I choose a different location, how about I choose this one? Now it is at a position of 1 meter. And if I start this, that 1 meter to the right, let's do it again, or to the left, that would be the amplitude of these oscillations. Okay? All right, so this is an example of simple harmonic motion because the spring force, if I go back to the notability, the spring force, that's what this part meant right here. A force that is directly proportional to the displacement of the box. And if you recall, the spring force is directly related to the spring constant that tells us how easy or difficult it is to stretch or smush the spring times X. So the spring force is directly proportional to where the box is at any instant in its movement. Going back to that animation. Okay, so like I'm going to keep this at x equals 1, and I'm going to pause it right here. Okay, one thing I want you to notice is right now the spring is going to pull the box to the left, but the amplitude is to the right. Now, if I look at the other extreme here, so now the spring force wants to push the box to the right, but the amplitude is to the left. So that's something kind of important. That's that restoring force, is that it always wants to push the box back to equilibrium, which I don't know if I can stop it right at the right moment. Not looking good. All right, fine, keep going. All right, so keep going like this. There we go. The force is always trying to push the box back to equilibrium, and right now the spring is at its relaxed length and the box is at the equilibrium position. All right, so now let's look at a pendulum. Okay, so here is a pendulum. Okay, so I can change the length of the pendulum. Like, let's go longer. Why not? Okay, and it says to click an angle to start the movement. So I'm going to click, how about 10 degrees? So the amplitude of these oscillations is 10 degrees counterclockwise, and 10 degrees clockwise, and 10 degrees counterclockwise, and 10 degrees clockwise. Now, if I reset this, that's the equilibrium position of my pendulum bob. Okay, now we can talk about how much time it takes to do one oscillation. So one complete oscillation would be from here That's a half. And then back to here. That's 1.5. That's 2. So if we measure the time for one oscillation, that's the period. And then we can take the inverse of that value to get the frequency. I didn't mention that with the spring, so let's go back to the spring. Okay, and let's play this. So one complete oscillation here, that's half, and that's one complete oscillation. Now we also could start, how about now, at the equilibrium position. So one complete oscillation would be now. Okay, you have to cover all parts of the oscillation for it to be a complete oscillation. Okay, now let's go back to this notability file. Okay, so just to make sure you have all the positions, right here would be the equilibrium. I'm going to zoom in here. This is the equilibrium position of the box spring system, equilibrium, right there. This is also right here the natural length or the relaxed length of the spring. Okay, but when we're not interested in the length of spring, we're interested in how much it is compressed or how much it stretches. So here, notice how we're measuring from the equilibrium position. The box has a displacement of 1 meter to the right. So that's my amplitude. Okay, and you can say plus 1 meter, or you can say 1 meter to the right. Now, we always measure from the equilibrium position. So here, when we squish the spring, so again, this is my equilibrium position, and now the box is 1 meter to the left. Or you can say negative 1 meter like it does here. But that is the amplitude. Now, at any position, so like, let's say I'm looking at a position where my box is, how about right here? That is not what I wanted to happen. Let's try it again. So here, let's say the box was right here. And notice we're measuring from the middle of the box. Well, this position is X. Okay, it's not the maximum X, or you can call it delta X if you like. But it's a position X, and if I wanted to know the force in the spring when the center of the box was right here, then you're not going to use the amplitude. You're going to use Kx. And as a reminder, the force right now at either position is to the left. The force out here at position P is bigger because my X is bigger. That's actually when my X is the amplitude, or X max, okay? But it works at any position X. Okay, so I think that's a pretty good start. So if something's simple harmonic, then the restoring force, which in this case is the spring, is directly related to position. So that makes it simple harmonic, and that's kind of cool. All right, I'm going to make another video where I explain to you the lab that you're going to do today. But thanks for watching. You have this video as a resource until you master all of this terminology. Okay, thanks for watching.